My name is Daniel. I am from the Chapel programming language team at HPE, and I'm here to talk about the challenges of growing the adoption of an open source high performance computing programming language, which is the Chapel programming language. So I'll basically start by introducing what Chapel is. We are a recent HPSF project, but I'll talk more about what we're doing. I'll then talk about why we find community building to be an important aspect of our technology, and in particular about community building for high-performance computing. And I'll wrap up by talking about the experience of our team, and in particular the three core areas that we found important while building a community. So what is Chapel? It's a programming language built from the ground up for productive parallel computing. And it's been, in my view, built up with two major philosophical goals that make it very well suited for writing parallel code. The first of these is the fact that Chapel puts parallelism at the forefront of its design. So while other programming languages enable you to do parallelism using extensions or libraries, in Chapel, the whole language has been designed with goals of enabling various sorts of parallelism, including like multiple tasks and multiple nodes, so distributed code, and that makes it well suited for those kinds of problems. Another main aspect of Chapel is its multi-resolution philosophy, which basically boils down to providing powerful and very easy to use tools to get parallel and distributed computing by default. But then, if these inevitably break down as the sorts of problems you tackle become more complicated, basically Chapel allows you to fall back to lower level and to mechanisms that basically give you more control. So here's an example of a Chapel program. This here in particular is doing the bail index gather benchmark, where really all you're doing is copying some data from a source memory buffer into a destination buffer, but you're reordering it a little bit. And so here there's destination and a source array, and also an array of indices, which tell you where to put something from the source into the destination. And this program here is distributed and fully parallel. So if you have multiple nodes set up, you will actually run this code and distribute the work across all available nodes and all available cores. Thanks to the block distribution on the second line of real code and the for all loop near the bottom. So now I'll talk about community building in particular, but first I think I should probably give a little bit of a context for our initial push for community building. So prior to really getting into community building, we tried to go for a big stabilization push, basically. The idea was that advertising a technology that breaks basically every release and forces you to rewrite your programs and adjust your solutions is just not acceptable. And because stabilization takes such a long time and takes so much engineering effort, here I have a discussion issue on GitHub that was one of the many discussion issues that we've had for the 2.0 push, which has 64 comments to discuss whether we should use special characters as part of reserved method names in the language. So we wanted to get through all of that before finally starting to advertise and push for a bigger community. And then once we did that, that gave us confidence to expand our reach and start working on community with kind of a full steam ahead kind of mode. And we believe community to be a very important piece of the puzzle for an HPC programming language, but also for HPC technologies in general. And I'll talk more about that in just a little bit. So I'll talk now about like some of our motivations for kind of trying to build up the community for a programming language. And these probably won't come as a surprise to you, but I just wanted to articulate them here. So the first is that members of a community can bring in technical expertise, and this can be done in two ways. So if you have a technical problem from a particular domain, like ocean science or something, well, we don't know anything about ocean science, but we do know how to get you computing your problems, solutions to your problems. And we kind of need a third party or an expert in their domain to work with. Also, building a community helps us shape the future direction of the language. So if we find that there's sharp corners that people repeatedly run aground on, we can now work to smooth these corners in the future. Also, coming from the perspective of a developer, I think we've heard several times today that kind of a sense of community and belonging is an important aspect for users. And so, of course, as a language kind of working towards adoption, we want to provide that. So if you write Chapel code, we want to be able to match you to other people who also write Chapel and who might have solved the same problems that you have, or maybe you can share their insights to help accelerate your own work. And finally, no one wants a single point of failure. No one wants a single vendor technology or something that's maintained by 3 people, and then if these people just disappear, then the technology dies, and everyone who uses it or relies on it is now kind of dead in the water. So building a community helps build resilience against these sorts of things, basically by providing a more engaged and broader user base. Now, the thing is, though, that I've talked about this from my perspective as a programming language developer, but if you take these same arguments and replace my programming language with your tool, these same things apply, and that's kind of what motivated me to give this talk. I think that in the HPC world in particular, all of us working on HPC technologies are kind of in the same boat here. And so all the arguments that I hope that most of the arguments that I'm giving here for community building for Chapel also apply to other HPSF projects. So now let's talk about some of the challenges. So for us, there are 3 relatively big challenges for building a community, and the first has been even like measuring success. So in particular, as an open source programming language just available on GitHub, it's very hard to get feedback about the size of your community. There's lots of proxy metrics like likes on social media, GitHub stars, downloads, and so on and so forth. But they're noisy, and it's dubious that they properly represent community size. And moreover, if you fail with your community building efforts, you very likely just hear nothing back from the community. And so you never know who you're failing to reach. And this is why I included this little picture of the airplane, where the planes that made it back with damage to particular parts represented by the red dots. But the planes that were hit in those areas never made it back, and so you never learned about them. For the plane, you can identify these crucial areas by looking at places where, if the plane was hit, it didn't make it back. But for something as nebulous as the community, it's kind of hard to identify things from the complement of things that you hear about. And finally, once you do get members, a key challenge is to keep them happy. You don't want to keep bringing people in and then be a revolving door where the people come in and they're like, well, this actually kind of sucks, and then they leave. And in particular, the HPC community, or building community for HPC, offers even more unique challenges. The first one is that HPC is a comparatively smaller field. I mean, certainly when talking to people just freshly entering the workforce, it's nowhere near as popular as something like web development, which has flashier results. It has more interesting, it has like a kind of a quicker ramp up to do things, and maybe it's even a little bit flashier. I'll jump to my third point here, which is that flashy results in HPC are hard to replicate. So, we'll do scaling runs. Well, we'll say, oh, well, we ran our program on 8,000 compute nodes. Well, fantastic. I have a laptop. How am I going to get any of those same results? And even when we say, oh, we were able to accelerate, a program by 5, 8, 6 times, whatever, those are relative to a particular machine. Like if you have, say, an old Chromebook, you're not going to get the same scaling, and so all these results are relative. Another key challenge is that HPC is driven by large legacy projects, at least in our experience, or the projects that have interacted with us. Say, a giant code base implementing some physics simulation, and people have spent lots of time polishing it and building that foundation. And for a new technology to come in and kind of demand a switch is a lot. Like, you have to really prove your value to budge these large projects and kind of get market share, I guess. At the same time, though, there's so much potential within the HPC community that I don't even think that we're reaching. And one of the main instances is that, practically every computer nowadays has parallel capabilities. Like, on the left here, I have the Steam hardware survey, and virtually no computers have only a single core. Most of them have multiple. And of course, lots of computers have GPUs, which effectively means that they come bundled with an accelerator. And if you have multiple GPUs, which some even gaming computers have, then you have multiple accelerators, and you're pretty much doing distributed programming. And so these same techniques that the HPC community has can apply to other people and to hardware that's accessible to more people. And so by growing the community of HPC tools, we can actually increase the size of the field, get more fresh blood, while at the same time helping experts who do already have access to this and already have a background in high-performance computing be more productive and make more efficient use of their time, resources, and so on and so forth. So now I'll talk about the things that we found to be important and also the things that we did to work in these areas. So there are the three core parts that I alluded to earlier, which is stability, learning resources, and developer tooling. Here, I think the focus on developer tooling primarily does seem influenced by the fact that we are a programming language, and so therefore do need kind of a bigger foundation of tools for users to make use of Chapel. But nevertheless, I think that these concerns are common among many technologies. And also, I started the background for this talk saying, like, we were waiting for a stable release of the language before we started building the community. And now here I have stability as one of the community building efforts. And the reason being is that stability is not a one-and-done thing. Like, you don't make a stable version of your product or project technology and just keep it like that. You have to allow for evolution. You have to maintain stability throughout. And so it's an ongoing effort for us, and I suspect for most technologies. And I'll just hammer down again on why stability is such an important thing. And the core aspect to this is that if you keep breaking code for everyone, you make them suffer. You know, if every 3 months Chapel releases, which is what we do 3-month releases, and you force people to rewrite parts of their code, you're forcing them to work on issues that are completely unrelated to what they normally want to do. And also, just because that requires engineering effort, you're effectively capping the size of teams that can work with your technology. Because, say, a team that doesn't have enough hours to dedicate to migrating between releases will simply not pick up the technology. And also, it makes organizations more hesitant to use something like that. Of course, if you change something and continuously break your technology, you also completely invalidate any documentation you've written or any sort of material that you've provided for others to help learn your technology. So, and we believe that to be important, and I'll talk about that next. Moreover, I mentioned how HPC has big projects, and that it's kind of the sort of thing that we run up against. And those big projects did not get there by building on unstable technologies. Like, you cannot have a big project if the foundation on which it rests keeps shifting. Also, if you're excited about AI, the fact that you keep breaking your technology is going to make any sort of trained large language model or something like that fall out of date constantly. And so you're effectively putting, you're capping your ability to provide users tools based on large language models or artificial intelligence to use your tech. But also, stability is important, but there's difficulties with using it, or with being stable. So you have to balance not breaking code with forward progress. Like, if you add new features and immediately guarantee them to continue working, you make it much harder to add something new. You make it much harder to innovate because every innovation needs to be tested for future stability. It can also make it harder to experiment. You can't just push out a feature that might not work and then see if it comes back, because that would break stability. You need to figure out a way to reconcile these two things. And here I have Hiram's law, which is all observable behaviors of your system will be depended on by somebody. So even if you fix bugs eventually, you might effectively be going back on some stability guarantees. Chapel tackles this with a concept of additions, which I'll describe very briefly, which effectively circumscribe a set of features in the language. And of course, we're a language, but it can also be a technology in general. So the idea is that there's a number of features, but only some of them are considered stable. And then there's a stable edition, which continues to exist as is throughout releases. And there's a preview edition where features can change or be added or be removed. And this basically allows people to early opt in to unstable features and test things out, and also allows you to build things in this unstable, in this preview edition and experiment with them without breaking the promises of a shared stable version. And eventually, of course, when you do need to innovate, you make the preview edition into the next stable edition and move on. So now I'll talk about learning resources. So I think that it's crucial for any technology to focus on learning resources because they provide answers to two important questions. The first is, how do I do the things that I know I want to do? And this is the clear value that I think we've seen in the earlier presentation here in this room. You need to demonstrate that the things that they already want to do, they've already done, can be done again and can be done either with the same amount of difficulty or simpler. And so this could be reading a file, getting some data on the GPU, communicating between nodes. It all depends on the final goals. But also, especially for technologies that try to experiment with new paradigms, you need to be able to tell people what makes you unique and what things they can do that they weren't able to do before. Kind of map the boundaries of what's possible. And so here learning resources are also important. I'm not going to go through the ways in which Chapel meets these criteria, basically. And a challenge with learning resources is that you can't just provide like one single manual and be like, all right, have at it, because different people have vastly different ways in which they engage with learning resources. Some people just cannot read large walls of text. And if you give them a manual, it's going to be a very unpleasant experience for them. And so something like a video tutorial or even an interactive session would serve them much better. Others, like me, hate watching videos and would much rather read some documentation. And so automatically there you have a conflict, and you need to do kind of both of those things. And if you're trying to access a new group of people, you need to tailor your documentation to these kinds of people, which again involves more effort and I think doesn't force you, but I think you have to put more effort to tailor documentation and to provide value to that new group of people that you're trying to reach. And if you're into AI, also written documentation helps provide context for large language models, which improves their performance. So if you want people to be able to use AI to interface with a particular technology, you'd better document it in probably a written way so far. And of course, an open question for us is, given all these different ways of providing help, how do we choose which we spend our limited time on? Here in the Chapel team, we've done a few things. We've ramped up posting on a technical blog. You can see here, this is a slide from Brad Chamberlain, the technical lead of the Chapel project. The little star, which might be hard to see, I don't really know, indicates the 2.0 release, and the arrows point to where certain articles were posted. Here, the 2.0 release was followed by a quick succession of various articles, and we're trying to keep that pace up as long as we have things that are interesting to say. We don't want to just publish for the sake of publishing. We also have expanded our reach by trying to hold interactive and kind of smaller scale sessions. So during ChapelCon, which is an event that we hold in which various Chapel programmers and people interested in Chapel can try to explore the technology, we've been holding dedicated coding days and tutorial days, which either host interactive sessions where you can just come, sit with your laptop, try to write some code, and have a developer be like, hey, this is good, this is bad, here's how you do this, and just get interactive assistance. And of course, we've also tried to split it out into small, bite-sized, kind of lighter weight and more practical tutorials to help people get stuff done. And of course, we've been trying to engage with people on social media, and I think that's all you need to see on this slide, really. And the final piece of the puzzle for us has been developer tooling. I think another law that I can quote here is that this is a famous one by Brian Kernighan. It's that debugging is twice as hard as writing the program in the first place. So if you're as clever as you were when you write it, how could you ever debug it? It'll be twice as hard. The corollary for HPC is HPC gives you much more power because you can do much more. You can use many more computing resources. You can use multiple nodes. You can use accelerators. But that also means that to debug problems in these areas, you also need much more power. And that leads to developer tooling. So you need to be able to kind of troubleshoot when things go wrong and not just wield power without any guardrails. There's a number of ways to do this from a technical perspective. There's static analysis, which happens before you run your code, and that's great because if you have a bug in your code and you wait 30 minutes in Slurm queue to launch your thread and then things crash, well, you've just wasted 30 minutes. So static analysis can help catch those sorts of things before it occurs. If you're into AI, you can also use static analysis to guide the AI faster towards the solution to a problem because it can iterate and catch errors earlier. Also without waiting 30 minutes in Slurm queue, but don't give your AI access to your Slurm queue. There's also runtime tooling, which gives you performance analysis, debugging, profiling, and all sorts of things. GDB is the canonical tool for C and C++, but I think that it falls short naively in distributed and accelerated environments. So you need ways with which to further help debug and troubleshoot high-performance software. On the Chapel team, since the 2.0 release, we've done quite a bit of work with the static sort of things. So we've worked on a language server which integrates Chapel with a text editor. Here I have some diagnostics shown to me in this is probably Visual Studio Code, but it works in other editors as well. And it's a little animated GIF of some common issues in Chapel code being automatically fixed by our linter. We've also done some work on debugging, which helps debug multi-node programs in Chapel with relative ease. But I won't talk too much about that because my colleague Jade, who's here in this room, is going to be giving a talk on Chapel tools. And if you're interested, you can go there. So my talk was titled Challenges with HPC Language Adoption, and I do not claim to have answers to some of the questions in terms of growing a community. But I'd like to leave off with some open questions to consider. So some of these questions are, what is the best way to reach an audience of people for HPC who are not traditionally interested in HPC? How can we broaden the interest and base of our field? Also, what's the best way to share and grow communities among projects as opposed to kind of siloed within a particular project group? And finally, how do we get these exciting results from HPC into a form that's replicable and accessible to folks with diverse hardware resources and basically available things to try them on? And that's my talk. Thanks for listening. I have probably a couple minutes for questions, but I'm not sure.
Okay, I'm going to ask you the first question. Okay. When you mentioned the editions, so you were talking about preview or whatever name you use and stable. Do you have a mechanism to sunset things that you want to get rid of?
Right, so effectively the stable edition, the things that we want to get rid of will persist and they will remain until eventually the editions will switch. But in the preview edition, these things might just start disappearing. So I guess the sunsetting mechanism is basically to say, to warn at first, to give a deprecation warning effectively and say, hey, this is currently there, but it's going to disappear, and eventually just remove it from that edition. And then finally that edition becomes the new stable edition, so that thing is gone for good and no longer supported. But that's a very long time horizon.
Yeah.
Go ahead.
So excellent talk, thank you. On your ending slide about open questions and broadening the community, so I noticed that I guess one of the 5 HPC carpentry workshops is on Chapel, and I was curious because I think that's kind of appealing, like to reach new users, right? I mean, it's very low effort from the user; they just have to show up to a workshop, and kind of you can look at them and make sure they're not distracted and actually doing the exercises. So I was kind of curious, like with the would there be interest with people from the HPSF in trying to have that in-person workshop capability, like more used or developed? Like I know you had like many different approaches in terms of documentation and developer tools, and I'm just kind of wondering how you kind of see that maybe playing a role or not.
I think that that's a very, very good way to build kind of a smaller scale, but more kind of direct and close interactions with people, right? Like a talk at something like ChapelCon is actually kind of less interactive than you'd imagine because, you know, you kind of broadcast the information and then you're not really sure if it was received, if there were any questions. You know, it's tough to interrupt the talk and be like, hey, what's going on here? Whereas something like a workshop is actually a very compelling way to see what's happening and also to see like the rough edges and the things that you're missing and to learn more about the audience that you're trying to reach. So I think that would be a very interesting way to reach the community. Thank you.
So I was interested in I think stability is one of the goals of a growing community for any programming language. And as I followed other communities who are trying to do similar endeavors, I've noticed that fragmentation can often become a big problem, especially like, for example, like async Rust, for example, nowadays, there's like a million runtimes, there's a million packages that all kind of strive to do the same thing or implement the same programming paradigm or same API. How do you guys take this approach for Chapel while still considering you want to value the speed in which you can implement these new features, but at the same time you don't want to stabilize these into a standard library or something and cause you to have tech debt later down the line?
Well, so there's a few things. With Rust in particular, I think from what I understand about especially the async thing is that it was meant as a foundation for async runtimes, right? And when you do something like that, you automatically open yourself up to competing implementations. And so far, we haven't done anything of the sort, right? So if we develop a feature, it's unstable perhaps, but it is, you know, canonical. So in that sense, we avoid fragmentation thereby. But if we want to like have new features, I think a compelling way is just to split them out into libraries, basically, which first of all, like, I think reduces the barrier to iterating on them and contributing, because as opposed to like getting into this whole thing and like digging in language internals, you have something that's kind of standalone and kind of smaller scale and easier to understand. I think it also encourages others who aren't as involved with the language as the core team is to experiment. So I guess those are the two things that. Does that answer your question?
Yeah, I think so.
Thank you.
Okay, let's thank the speaker.
Thank you.